You usually expect finding information to be, a clean process, right? You type a query into a search bar, hit enter, and there is the answer.
Right, found or not found.
Exactly. Precision engineering.
Yeah, but that clean binary completely falls apart when you step into the world of nuclear regulatory compliance. I mean, you are no longer looking for a simple keyword match. You are trying to synthesize a holistic judgment from this absolute mountain of highly technical, disjointed evidence.
And that is exactly why we are here. Today's deep dive is for those of you listening who want the massive, aha moments of AI research without having to decipher the dense academic jargon yourself.
Which is definitely a plus.
Right. So we are looking at a state-of-the-art paper, a SOTA paper, that tackles one of the most high-stakes, information-dense challenges you could possibly imagine. Our mission today is to explore how artificial intelligence is, evolving past basic search and summarized tools.
Yeah, moving into active, autonomous agents that are capable of genuine planning and reasoning.
Okay, let's unpack this. We are talking about multimodal nuclear regulatory documents, which sounds intimidating, but the core problem is super relatable.
It really is. We are looking at a fundamental shift in how a machine processes information. The underlying challenge here is navigating a 10,000-page haystack.
Wow, 10,000 pages.
Yeah, and the needle you are looking for is broken into pieces. One piece of the needle is in a regulatory chapter, another is in a data table, and a third is hiding inside an engineering blueprint.
To really appreciate how this new system solves that crazy puzzle, we have to look at why the AI tools most people use today fail so miserably at this specific task.
They really do fail.
I mean, if you use a corporate AI system today, it is very likely running on RAG, right? Retrieval Augmented Generation.
Exactly. And the standard RAG pipeline relies on a process called chunking because, an AI cannot hold an entire 10,000-page document in its active memory at once.
That makes sense.
So the system effectively shreds the document into small, uniform paragraphs. It converts those chunks into mathematical vectors.
Okay, so just turning text into numbers, basically.
Right. And when you ask a question, the system searches for chunks that share semantic similarity with your prompt. It pulls them out of the pile and feeds them to the AI to generate an answer.
And that vector similarity search makes total sense if I am asking a simple question about, a company policy. It just finds the paragraph about vacation days.
Exactly, a straightforward match.
But a final safety analysis report for a nuclear reactor, it does not work like that at all. The answers depend entirely on cross-referencing.
Absolutely, entirely.
You might have a highly technical table in Chapter 5 detailing pressure valve tolerances. But that table only makes sense if you apply the safety requirements detailed way back in Chapter 1.
And chunking completely destroys those cross-references. When the vector search pulls the table from Chapter 5, it just leaves Chapter 1 behind.
Because it doesn't look like a match.
Right. The text in Chapter 1 does not mathematically resemble your specific prompt about the valve. So the AI sees the table, but has no idea what the underlying rules are for interpreting it.
It is like trying to solve a complex murder mystery. But instead of letting you read the book chapter by chapter, someone rips out random paragraphs, scrambles them up, and hands them to you based on how many times the word blood appears.
That is a great way to put it.
You completely lose the causal context.
You do. And the researchers actually benchmarked this failure. They tested advanced systems that attempt to solve this by building static maps of the shredded text, which is known as offline indexing.
And how did those do?
Not great. A system called GraphReg scored only 49.5% accuracy on their nuclear document benchmark. Another system, LightRag, hit 73%.
Wow. So those systems fail because they are trying to pre-compute every possible relationship in the document before you even ask the question.
Exactly. They lack an iterative, step-by-step judgment loop. They build this massive static web of information.
Which sounds good in theory.
It does,
yeah.
But it introduces a fatal real-world problem. Offline indexing is fundamentally incompatible with documents that are continuously revised.
Oh, because it's static.
Right. You cannot spend hours and massive amounts of compute power rebuilding your entire semantic graph every single time an engineer updates one paragraph in a 10,000-page file.
So shredding the document into vectors does not work. And pre-computing a massive static map takes too long and still misses the nuance.
Yep, both fall short.
So we need the AI to navigate the live document the way a human nuclear inspector would.
And that is where the breakthrough happens. The researchers stopped treating this as a retrieval task and modeled it as a sequential planning problem.
Okay, planning?
Yes. They equipped the AI agent with tools modeled directly on a computer file system. It has a browse command, similar to listing a directory, which lets it view tables of contents and section hierarchies.
Oh, nice.
It also has a read command to pull up the full text of a specific target. And it has a search command to hunt for exact keywords across the entire corpus.
So if it's treating this like a file system, it must be running commands dynamically. How does the AI actually choose which tool to use at any given moment?
So the large language model acts as the reasoning engine. When you ask it a question, it doesn't just blindly fire off a search. It looks at its current goal, looks at the tools available, and generates a structured command.
Right.
As it executes these commands, it builds what the paper calls a dynamic subknowledge graph.
Which is essentially the AI's short-term memory growing inside its context window, right?
Exactly. It creates literal nodes of evidence. So it might use browse to find chapter 1, use read to extract the seismic rule, save that rule as a node in its short-term memory, and then realize, okay, I have the rule.
Now I need to find the pump.
Exactly. Now I need to search for the specific water pump to see if it meets this rule. It plans its next move based purely on the accumulated state of that subgraph.
The results of this sequential planning are wild, by the way. On a 200-question benchmark built from actual NUS-scale nuclear reactor documents, this planning AI achieved an 81.5% accuracy.
Which is a massive jump.
Right. And to prove how crucial the planning aspect is, the researchers ran a baseline test called Page Index. Page Index had access to the exact same browse, read, and search tools.
But it didn't have the memory.
Right. It did not maintain that dynamic short-term memory state. It just fired off searches.
And the performance gap there is probably the most telling data point in the entire paper. Page Index scored 43.5%. The planning agent scored 81.5%.
That is huge.
Giving the AI the ability to hold a state and plan its next move based on what it just learned created a massive 38.0 percentage point improvement.
Wait, hold on, though. If you give an AI the freedom to just keep executing browse and search commands across millions of words, I mean, it's going to get lost in an endless rabbit hole.
That is a very valid concern.
Right, because if you let me loose on Wikipedia with those tools, I start researching nuclear physics, and 3 hours later I'm reading about the invention of the toaster.
We've all been there.
So how does the AI avoid burning massive amounts of compute time reading about irrelevant valve histories?
If we connect this to the bigger picture, it utilizes a mechanism called a sufficiency check. And this is where the system mimics human cognition beautifully.
Okay.
The AI operates on a loop with a maximum budget of 4 hops. But before it initiates the next hop, before it clicks another link or runs another search, the LLM is prompted to evaluate its current subknowledge graph against the user's original query.
So it essentially stops and asks itself, do I already have enough evidence to defend an answer?
Exactly. It evaluates its own homework. If the sufficiency check passes, the loop terminates immediately. And the data shows that 33% of the queries terminate early, well before hitting that 4-hop limit.
Wait, does early termination mean the AI got confused and just gave up?
No, the exact opposite, actually.
Yeah.
The queries where the AI stopped early achieved an 85.5% accuracy rate.
Oh, wow.
Yeah, and the queries that required the full 4 hops dropped to 78.3% accuracy. The system is incredibly well calibrated.
It knows when it's right.
Exactly. It terminates early on the straightforward regulatory questions because it genuinely recognizes when it has synthesized the correct answer.
Okay, but a nuclear reactor isn't just text. We are talking about highly technical flowcharts and complex engineering blueprints.
Very complex.
Right, so if the AI is only building a text-based short-term memory using commands like read and search, what happens when it hits a 20-page visual schematic? Standard text AI is notoriously bad at interpreting visual data.
Oh, absolutely. In document analysis, this is known as the figure on a different page problem. You are reading a dense paragraph on page 84 that says the structural integrity is maintained as shown in figure 5.11.
But that visual figure is sitting way over on page 91.
Exactly.
So if you were building a text chain, you've completely divorced the description from the actual image it refers to.
Right. And the naive engineering solution would be to process the entire 10,000-page document using vision language models or VLMs. You just feed every single page, images and all, into a massive neural network capable of seeing the pixels.
But running a VLM on every single search step for a document that size would bankrupt the project.
Oh, completely. The latency and compute cost would be astronomical.
So what do they do?
Well, the researchers engineered a brilliantly cost-effective workaround. All the intermediate searching, browsing, and planning remains entirely text-only.
Okay.
To bridge the gap to the images, the system runs a parser over the document beforehand. When the parser detects an in-text reference, like see figure 5.11, it automatically injects a metadata link tying that text to the exact coordinates of the PDF page where the image lives.
Oh, I see. So the AI's short-term memory just holds a placeholder link. It knows the image is vital evidence, and it knows exactly where it is, even though it hasn't actually looked at the pixels yet.
Yes, it builds the entire logical evidence chain in cheap, fast text. Only at the very final step, after the sufficiency check is passed and the AI has decided it has all the necessary pieces, does the system render those specific, targeted PDF pages into images.
That is so smart.
It is. It then feeds just those images to the GPT 4.1 vision model to generate the final synthesized answer.
And what about the tables? Because some of these regulatory tables span multiple pages with incredibly complex headers.
The system is even more efficient with tables. It completely bypasses the vision model for them.
Really?
Yeah. It extracts the visual grid structure of the table and converts it directly into structured text, like Markdown. And a standard, cheaper language model can read Markdown perfectly.
So what does this all mean for you, the listener? It means cost efficiency. The cost efficiency of this hybrid multimodality pipeline is frankly hard to wrap your head around. By keeping the intermediate steps text-only, the system yielded an 86.0% accuracy on questions that only relied on tables.
Which is incredible.
It completely crushed the previous state-of-the-art model, Raptor, which only managed 68.0%.
And the economics of that performance are a critical part of why this paper matters so much.
Because the researchers ran the entire 200-question benchmark. We are talking about multi-hop, highly complex nuclear regulatory questions requiring synthesis across text, tables, and blueprints.
Right.
And the total cost of the computing power for the entire test was about $46. That is roughly 21 cents per query.
It's basically nothing.
Compare that to a highly trained human nuclear engineer billing over $100 an hour, spending 2 or 3 hours tracking down cross-references to answer a single conformance question.
The comparison is wild.
A 21-cent autonomous AI query that gets it right over 80% of the time is a staggering value proposition.
It really is a phenomenal leap in capability. But it introduces the final hurdle of deploying AI in safety-critical fields. I mean, in the nuclear industry, you cannot just be cheap and accurate.
You have to prove your work to the regulators.
Exactly. The industry is bound by strict traceability rules, specifically the Code of Federal Regulations, 10 CFR 50 Appendix B.
That sounds intense.
It is. If an AI agent just outputs a final paragraph saying, yes, the reactor design is safe, federal inspectors will throw it out, they need an auditable trail of the exact logic used to reach that conclusion.
So how does a neural network, which is essentially a giant black box of probabilities, prove its logical work to a human auditor?
The researchers introduced an optional module called post-retrieval edge inference. To understand this, look back at the AI's short-term memory. That knowledge graph filled with nodes of evidence we talked about.
Right, the node.
This module takes an extra step. It looks at 2 nodes of evidence and explicitly defines the edge or, the logical relationship between them.
Okay, so how does it do that?
It does not just say node A and node B share keywords. It generates a human-readable label assigning a logical verb. It states node A satisfies node B, or node A supports node B.
It is dynamically generating a literal map of its own reasoning for the human auditor to follow.
Yes.
But you mentioned this module was optional?
Yeah, it is optional because running this specific relationship inference adds about 2.8 times more to the total compute cost. And interestingly, generating these explicit edges doesn't actually boost the AI's accuracy in answering the question.
Wait, really? It costs almost 3 times as much and doesn't make the AI any smarter.
Well, the sequential planning loop is what makes the system smart. The edge inference module exists entirely to make the system auditable, which is a non-negotiable requirement for deployment in these environments.
That makes sense.
And the data this module produced during the benchmark is fascinating. Out of 7,391 logical connections the AI made, the system generated exactly 3 edges labeled violates.
Just 3?
Yes. That is a violation rate of 0.04%.
Wait, it found 3 violates edges in a document describing a nuclear reactor? Because the document they tested, the NuScale Final Safety Analysis Report, has already been certified by the U.S. government.
Right. It is an approved, compliant design.
So if the human regulators already stamped it as safe, did the AI uncover fatal design flaws they missed?
No, it found something much more nuanced than a fatal flaw. It flagged complex scenarios that require high-level human judgment. 2 of those violates edges were instances of the AI identifying what engineers call scope boundaries.
What does a scope boundary look like in the context of these documents?
Well, for example, The AI pulled up the specifications for a chilled water system. It evaluated those specs against the strict seismic safety requirements and correctly noted that the water system failed the seismic test.
A basic search tool might flag this as a massive emergency.
Exactly. But this AI also read the surrounding context, which explicitly stated that the chilled water system is non-safety related. If an earthquake destroys it, the actual nuclear core is unaffected.
So the AI isn't finding a dangerous violation. It's successfully identifying that a specific safety rule intentionally does not apply to that specific piece of equipment.
Spot on. It accurately mapped the boundary of the regulation.
And what about the third one?
The third violates edge was even more subtle. It involved a specific steam generator design. The design completely eliminated a traditional leakage problem, which is great for safety. But in doing so, the new design slightly limited how effectively inspectors could detect certain types of new leaks. The AI flagged this logical friction as partial conformance.
Which is exactly the kind of highly technical gray area a human inspector needs to spend their time reviewing.
Yes, this raises an important point. The AI is not designed to replace the human reviewer making the final call. It is designed to act as a targeting laser.
Right, pointing them exactly where they need to look.
Instead of forcing a human engineer to manually read 10,000 pages to find potential issues, the AI tees up those 3 specific edges out of over 7,000. It points the human directly to the 3 paragraphs that genuinely require a domain expert's judgment.
Here's where it gets really interesting, though. When you look at the times the AI was technically wrong on this benchmark, the numbers get even more impressive. Out of 200 questions, the judges marked 38 of the AI's answers as incorrect. But when the researchers performed an error analysis, they found that 29 of those 38 errors were simple phrasing mismatches against the grading rubric.
Oh, it is the classic problem of an automated grading system penalizing a correct answer for using the wrong vocabulary.
Exactly. The grading rubric expected the answer to be the pressurizer volume is 578 cubic feet. The AI generated the answer, the pressurizer region volume is 578 cubic feet.
So close.
Right. The judges marked it as a failure because of the extra word region, even though the AI synthesis of the technical data was flawlessly correct. When you strip out those semantic technicalities, the actual deployment-relevant failure rate of this AI system drops to an incredible 4.5%.
Furthermore, the hallucination rate, where the AI simply invents facts out of thin air, which is a major concern with language models, was a microscopic 1.0%.
Wow, 1%.
For a system autonomously navigating tens of thousands of pages of cross-referenced nuclear codes, blueprints, and tables, that level of reliability proves the architecture works.
We are truly witnessing a complete paradigm shift. We are watching AI evolve from a glorified index card system into an active, state-aware agent.
It really is a new era.
It can plan its own path through a file system, it evaluates its own knowledge to judge when it has enough evidence to stop, and it synthesizes complex text and multimodality data, all while generating an auditable, human-readable proof of its logic. It fundamentally redefines how we can process massive data sets.
It proves that if you design the right environment, if you allow an AI to browse, read, and search dynamically based on its own short-term memory, rather than just feeding it mathematically similar shreds of text, it can conquer some of the most complex reasoning tasks we have ever created.
I want to leave you with a thought as we wrap up today's deep dive. We just spent this time looking at how an autonomous AI agent can navigate 10,000 pages of highly classified hyper-technical nuclear codes to find a tiny instance of partial conformance in a steam generator.
Right.
But what happens when this exact technology leaves the nuclear lab? Imagine unleashing the sequential planning loop on your own life's complex paperwork.
That is a fascinating thought.
Imagine pointing this AI at your massive, convoluted medical history across 5 different doctors, or a 50-page mortgage contract, or one of those endless corporate terms of service we all just click agree on without reading.
Everyone does it.
If an AI can find the subtle violates edge in a nuclear reactor's chilled water system, what hidden clauses, contradictory requirements, or vital connections might it uncover in the documents you sign every single day? We started this conversation talking about finding a needle in a murky 10,000-page haystack. It turns out AI isn't just getting better at finding the needle.
No, it's not.
It is learning how to tell you exactly how that needle was made, how it connects to the rest of the haystack, and whether or not it's going to poke you. Something to think about the next time you hit accept.